So good afternoon to everybody. I hope you can see my
Yeah,
screen.
everything good.
Okay, that's great. Yeah, so thanks for the invitation and introduction. Uh, is it working? Okay, I'm coming from the HiLASE Laser Center in Prague. So we are like a technological center of the Institute of Physics of the Czech Academy of Sciences. Yeah, we are south of Prague. Probably many of you know us, and we are focusing on like development of laser technology and laser application, and we are focusing also on technology transfer to industry. The key technology which we are focusing on is femtosecond thin disk technology, which is based on fully in-house developed solutions. And the Bivoj laser, that's like a name of kilowatt class nanosecond diode-pumped solid state laser. We've been developing in close cooperation with the STFC in the UK. So finally, we managed to generate 1.5 kilowatt, 150 joule pulses from that system, and I would like to focus on a bit more details during my talk here. The cryogenically cooled diode pump solid state laser Bivoj, it's a result of many years of development. The system itself was commissioned at HiLASE in 2016. However, since that time, we are gradually upgrading it. And actually, lately, there is demonstrated pulse energy 150 joules at 10 Hz repetition rate in pulses which are like tunable from 2 to 40 nanoseconds. The laser is based on like the dipole or mercury technology, so that means we are using cryogenic cooling of several slabs made of ytterbium, which are cladded by chromium acceptable absorber. And up to now, it's still most powerful laser with the pulse energy of 1 joule in the field of that pumped solid state lasers. Yeah, so you see here the like footprint of the laser system. It consists from the front end on the right side and two energy boosters, power amplifiers. Yeah, the amplifiers are both based on the multi-slab technology. The first amplifier contains 4 slabs of ytterbium with different dopant concentration of ytterbium. So they have size, they have like 45 millimeters and 5 millimeters thickness. The beam size in the first amplifier is 20 by 20 millimeters square, and it's a 7-pass amplifier pumped by laser diodes at 940 nanometers. The second amplifier then contains 6 slabs. Again, it's a multi-pass setup, diode pumped. Both amplifiers are cooled by the helium flow, which the helium flows between the slabs of the amplifier, and the working temperature is 150 kelvins. The slab size in the second amplifier is 100 by 100 millimeters square, and we are using the largest ytterbium ceramics ever made, like in the world. Yeah, so it's like quite unique technology. And to the results, so we lately achieved 143 joules in like yeah, so here you see the 60 minutes test of the amplifier. You see the output is relatively stable. We have like no drop of energy, nothing like that. Optical to optical efficiency is approximately 30%, and you see near field and far field beam profile. Still, there is some space for improving the far field profile, so we are working on deformable optics, which will be installed in the system. And yeah, in fact, yeah, this upgrade to 100 and almost 50 joule was possible due to development or because of development of new optical coatings, which are able to withstand 5 joules per centimeter square for large size LIDT. So it was a cooperation of HiLASE and optical companies. We were able to do the large size LIDT and develop this like new kind of coatings. Yeah, so the size of the beam you are using for your LIDT test is extremely important in the field of these large size lasers. So the beam itself from the Bivoj laser is squared with flat top energy distribution, as you see in the first row. So we integrated a spatial light modulator for improving, besides some apertures, for improving the profile. But because of that spatial light modulator, we are also able to change the beam to circular, for example, do not, and maybe some other ones. The beam can, or the laser pulse, which is, as I mentioned, nanosecond, can be also shaped in time. So we can change the pulse duration from 2 to 40 nanoseconds, and it can be like flat top, shock compression, RAM, double pulse, or whatever you need for your applications. So one of the key applications for our laser is like laser shock peening, hardening of material surfaces by shock wave. And this one is like extremely important option for optimizing, for example, the laser shock peening. Yeah, other applications are, for example, laser induced damage threshold measurement and some other one in like particle physics. What is like unique for the Bivoj system? Usually in the large beam, high power systems, you have problems with depolarization losses. So that's the case also of the Bivoj laser. We were suffering from very high depolarization losses in like unoptimized system. The losses were higher than 50% of pulse energy. You see in the first slide, first row. We were able to develop a set of like 4 wave plates, 2 in front of the system, 2 after the system, and the proper combination of the wave plates is enables us to reduce the polarization losses down to 3% only. So it's like a quite unique way. So it integrates polarimetry, and we developed like a predictive algorithm which helps us to set the position of the optics, because otherwise we have 10 hertz repetition rate, so otherwise it would be task for a very long time and like playing with very expensive systems. So we are able to predict the exact position for all the wave plates, and we are able to do the same also for other laser systems. So we are testing this also at other lasers and are able to offer this service also to our colleagues at other large facilities. Thanks to the very good homogeneity and uniformity of both the profile, the beam profile, and the polarization, we were able to convert the output to second harmonic frequency with very high efficiency, 75%, and the peak 80%. So you see also the stability of the conversion is very good after some thermalization. And that's the next world record we reached, 95 joules at 10 hertz at 515 nanometers. So we used LBO crystal for this conversion, type 1 at 30 degrees centigrade. So you see here the output is very stable, and this is the near field beam profile at second harmonic. The same at third harmonic. So we reached also very good output, almost 50 joules at third harmonic, which is also the record at 343 nanometers, 10 hertz. So the efficiency is 55% of the conversion. So it's a sum frequency of second and fundamental. We have very good stability of the output, like 1% RMS. Still, we are working on homogeneity. It's caused by some like thermal gradients in the crystals. So you see after 60 minutes, there is some small change in the near field profile. So that's what we are further optimizing. And again, we use LBO crystal for this conversion. And the very last thing I would like to mention for this system, we also developed a Faraday isolator. There is no a system like that available on the market. So it's also fully in-house design at HiLASE. So it uses TGG crystals with compensation, like a partial compensation of thermal stress induced by effulgence by quartz rotator. It contains cooling by airflow. Yeah, so there are several slabs, 2 slabs of TGG, 1 slab of the rotator, and we are cooling it by airflow. This is how it looks like. So this magnet which has 3.5 Tesla in the center, and these are the slabs of TGG, the upper figure, and you see the optical scheme of the setup. We were testing it up to 1 kilowatt, 100 joule 10 hertz up to now. So with the TGG crystals, you see we were able to reach 30 dB or more than 30 dB isolation ratio for a very long time operation. And we repeated later the same test with the ceramic TGG. The results were comparable. The isolation ratio was around 30 dB. Yeah, so it's working in an excellent way. And that's something, yeah, so this like experience, that's something what we can offer also to our partners. So the main applications for this laser are, for example, like industry application. It's a perfect tool for industrial laser shock peening process, analysis of laser-induced damage threshold of plenty of materials. It can be excellent driver for OPCPA system. Yeah, so we are negotiating now or cooperating with the Eli beamlines in Prague about the OPCPA and its development in the future. And it can be also like a perfect nuclear fusion driver. Maybe it's like a diode pump technology with 10 hertz repetition rate. So there is high potential in future upscaling, maybe for this kind of applications. Yeah, so thank you for your attention. And if
Thank
you
you,
have some
Martin.
question, yeah, I am open to answer.
Yeah, we have
Thank you.
time for questions.